Alright, question 4, 5, and 6 for the long answer part. Question 4 deals with normal probabilities, things that are normally distributed, finding percentages or probabilities in there. Okay, so the heights of Who's down Whoville are normally distributed, mean 62 inches, standard deviation of 4.5 inches. So we want to determine the percent of Who's taller than 70 inches. Alright, so we got a bell curve because of the normal distribution, and the mean is 62, and we're looking to see how many people are taller than 70. So this is giving us a basic idea how this works. So we got 70 right here, some number above the mean, and we're looking to find that area right there. Alright, so that's basically what we're being asked to do. Now remember, in this case there is none, so we put 999, and then the mean, which is 62. Alright, and then the standard deviation, which was 4.5 inches. Alright, and that area from this picture is equal to 0.0377. So our answer to part A, 0.0377, but they want it as a percentage, so we need to change that from a decimal to a percent. So 3.77% are taller than 70 inches. Alright, then they want to know if there's 1,500 people who live in there in Whoville, how many of them are going to be at least 70 inches tall? Alright, so all this is basically asking you to do is take your percentage that you got from the last part and multiply it by 1,500. Alright, in percent problems usually means multiply, so 3.77% of the 1,500 will be above 70 inches tall. So 3.77 times the 1,500 would be 56.58. So that would round to nearest whole number 57 Who's. Alright, and then part C just gives us a different number in different direction. So how many would be less than 58 inches tall? So shorter than 58 inches. Alright, that would be down here below the mean, 58 somewhere, and now we're looking for this area below the mean. So again, drawing a picture helps, because when you're doing normal CDF, again, you're asking yourself, where does the shading start? The shading starts way down here somewhere. Is it to a percent? Which they do ask us to, so we should. Alright, so next one, 5. Is there an association between eating ice cream and automobile accidents? Well, there shouldn't be. Eating ice cream and automobile accidents, unless you're maybe doing it at the same time, there shouldn't be a link here. So, but we're expecting maybe a small r value here, but we still need to run the analysis to see. Alright, this is scoops per week. It's measured in hundreds, and this is automobile accidents per week, also measured in hundreds. So this would be 820, 1,180, 1,040. Alright, these are in hundreds, so you have to basically multiply these numbers by 100. Alright, so you don't have to give your data set. You can just put in what you see there into your stat editor. We got list 1 and list 2. Alright, and just run your data, put all your data in there, and then we'll calculate R. Alright, now I got all my data in. Once I have my data in, remember to calculate R, you need to run your not your one variable stat, it's your linear regression. So I'm going to run the linear regression, and I'm going to get R is equal to negative 0.1171, right, to 4 places. So R equals negative 0.1171. Alright, don't forget your negative signs. Remember, R can be positive, but it will also be negative. R squared, right? Remember, R squared is always positive, A, because it's squared. It's the square of R, and any value that's squared, positive or negative, will give you a positive number. Alright, so R squared right there above it is 0.0137. But we usually write R squared as a percent, so 1.37%. Alright, what percent of variation in Rex per week can be attributed to factors other than ice cream? This is just the percent of variation that is attributed to ice cream is R squared. So 1.37 is attributed to ice cream. So the percent that is not attributed to ice cream, or factors other than ice cream, is 100% minus whatever R squared is, which is 1.37%. Right? So that gives us 98.63% is explained by something other than ice cream. Right? Which, again, that basically means everything. Almost everything is explained by something other than ice cream. The amount of ice cream eaten per week should not explain how many Rex there are per week. So that's why we're getting this really low number for R squared, and that's why we're also getting a low number, or a high number, that is, for our answer for part C. Alright, determine the linear model relating Rex per week and scoops per week. That's just saying plug in A here for this A and B for this. So y equals negative 0.0. So there's our linear model that relates Rex per week and scoops per week. Alright, now part E wants us to estimate the numbers of Rex in 1 week if Morgan sells 800 scoops. Alright, if they were to sell 800 scoops, we would technically plug in the number 8, not 800, but 8, because it's in hundreds per week. So these numbers are in hundreds per week. So we would just put in 8, but we would also want to make sure that this is linear, the correlation, that this is satisfactory to use this model. Remember, we compare this R to that critical R from this table, A5 in your book or in the foldout, and we look at how many data points we have. So again, we have 1, 2, 3, 4, 5, 6, 7, 8 pairs of data. So that means that n equals 8. So if we were testing an alpha equals 0.05, R would need to be bigger than this. If we were testing an alpha equals 0.01, R would need to be bigger than this. Right? It doesn't tell us what alpha to compare it to, but it doesn't matter because R is not going to be bigger than either one of those in absolute value. So that means that we can't use, or we could use the model, but they're not linear related, so there's no point in using the model. So we're just going to use the mean of the Rex per week. So remember, if you have two variables, you don't use one variable stats, you use two variable stats. Right? And I clicked on one. You use two variable stats. And we're looking not for the mean of the x's, but we're looking for the mean of the y's. So 7.475 is the number here, but once again, remember, this is in hundreds, so 7.475 is actually 747.5 number of Rex, alright, which we would round to 748. So we would estimate 748 Rex if that many that many scoops were sold. We would just expect the average, right? Because they're not linearly correlated. We don't have any other reason to believe anything other than the average would happen. Alright, and then 6, the last one, the hypothesis test problem. Okay, so last year Facebook claimed a typical user is on average online for 53 minutes a day on Facebook. The people behind the scenes want to determine if the popularity of the site is different, right, not equal to the 53 that it was last year. So they take a sample of 100 users selected, and a sample mean of 55 minutes per day is produced by that sample of 100. Alright, they want to come up with, they want to test the claim. Is the number of average minutes spent online the same as it used to be. Alright, so our claim is going to be H naught is the mean still equals what it was last year, 53. Alright, and H1, our alternate hypothesis, is the mean is not equal to 53. Again, they told us to use not equal, different. Okay, so mean is equal, mean is not equal. Determine the test statistic. How do we do that? We run the test, right? That's how you get the test statistic. Alright, what type of test is this? So you ask yourselves a question. Is this hypothesis test about a proportion? No, it's about means. Alright, so it's Z or T. Do I know the population standard deviation? No. I only know the sample standard deviation. So this is a t-test. Alright, do we have data or stats? We have stats. What's the claim mean? The claim mean is 53 minutes, what it used to be. What's our sample mean? Our sample mean is 55 minutes. Our sample deviation is 15 minutes per day. And our sample size was 100 users. Right, this is a two-tailed test, or a not equal is your alternate hypothesis. So that's this one, and now we tell it to calculate. Alright, so the t-value, that's your test statistic. The very first thing it returns is the test statistic. So the t-value here is 1.333. Alright, to two decimal places, 1.33. Alright, determine the critical value given alpha equals 0.05. Remember, your critical value is in a t-test is given by the table. So, alright, here is our critical t-values. This is a two-tailed test because of the not equal to. Alright, and they tell us our critical value is, or our alpha value is 0.05. So we're using 0.05. Right. Our degrees of freedom, there's not a 99 on here, so we use the closest one to it. So the 100 is the one we're going to use. So for a 0.05 test, which is kind of standard, that's why it's in bold, we're going to use the 1984. Oops, 0.4. So there's our critical, 1.984. So there's our critical t, 1.984. Right, and it wants us to determine the p-value. Remember, the p-value is right underneath the test statistic. The very next thing down is the p-value. So the p-value is 0.1854 or 0.1855. Alright, and clearly state our conclusions. The last thing, remember, if p-value is less than alpha, we reject. If the p-value is greater than alpha, that means we fail to reject. Alright, so because the p-value here is greater than alpha, 0.1855 is greater than 0.05, then we would say we fail to reject that the average amount of time a Facebook user spends on Facebook is different than 53 minutes per day. Alright, our data did not support that alternate claim. Alright, so there is your practice final. If you have any questions on it, let me know.